So it's so the person who came up with this. So if data has distribution. Distribution, let's say inside it has probability. The person who came up with information provided by observing xi is log pi. Okay. Usually you write base 2. Okay. And so let's say I had no idea what I was going to expect, okay, and I observed xi. So the uncertainty is probability pi, right? Right, because I don't know what I was going to accept, but I see something with pi. Or you can think of it this way: if something was going to happen with probability 1, then there is no information. If it's, you know you're expecting it, probability 1. So if you put 1 in here, what you get is 0. The lower the probability, and you observe it, it's unexpected. Huh? Unexpected, or uncertainty revealed. So the lower this value, I should put minus sign. Lower this value, the more information you get. Okay? And this is what I could just say. So you said, how does this relate with bits? Okay? So I'm just going to give you a sort of not a theoretical, but sort of as an example. And the example that I gave was tossing of the coin. Tossing of the coin. The tossing of the coin, it's either heads or tails, right? So if in the coin situation, so probability of head is a half, right? So how do you represent that you got a head in terms of bits?
0, 1.
Or, if I quantify this head as xi, I could represent that as 0. Or I could quantify this as 1, whichever is your convention. If that's head, then I could say x. I could just give it any number. I could say this is head and x million is tail. X, whatever number I can give, and it doesn't matter, right? Half, right? Because the event space, I hope the prerequisite for this course is, by the way, it's probability, right? The event space is all possible outcomes, right? The outcome is either head or tail, right? That's 2 outcomes. And how do you represent head or tail? It's by convention, right? I could call head as x equals 0, x equals 1, or I could call it x equals minus 1,000. It doesn't matter, right? that's not. But it happens with a probability of, let's say, half a fair point. So that was the sort of uncertainty. And you asked me a question about how do you quantify, how do you relate this with bits? The information that is obtained by observing head is this, okay? I could actually put any basis I want, okay? But if I use 2, that would quantify as bits. One question, right? Or 1 bit, okay? Or you could think of it this way, bits, how many questions would I need to ask to determine the observation? That was probabilistic. You could think of it that way. And that's represented as bits too, right? Right? How many questions? Let's say 4 questions. So what would that be? No? 2 bits. 4 questions, right? 2 bits. How many questions? 10. Yeah. Or let's say a good number would be, let's say 8 questions, then it would be 3 bits. Right? 3 questions to reveal what it is. How many questions? And then you take the log base 2 to represent that in bits. Does that make sense? How many questions? And then that number, take the log base 2.
That makes sense when we have natural number of bits, but not we have right now rational number of bits. And
You mean not integer numbers? What do you mean by 1.5 bits?
yes.
1.5 bits. You can think of it this way. Let's say let's take for instance 1.5 bits. Okay. If I observe that observation 10 times, 10 times, how many bits would that be? If each one is 1.5, that's 15 bits. .5 means just take the times 10, right? How many bits? That's 15 bits. Okay? So that's sub-integer values. That's what I think you were asking. Okay? I'm sorry I cannot go into detail more than this because this is not a course about entropy. This is so I have a lot of other materials that are based on this. So I just want to, I'm hoping that this concept of entropy is taught in communication, because in communication entropy is very, very important. Probability, okay? So I'm just going to stop at this. But there are lots and lots of information on the internet. Okay? So I hope this sort of answers your question to a certain extent. Okay? So, entropy. Regarding reference, I would suggest that, so I've mentioned Introduction to Machine Learning by Etham. There were a whole bunch of references to which I went through. There was an easy book that I mentioned, the easiest one, okay? Introduction to Machine Learning. That's something that you can read. Tom Mitchell's book on machine learning, that's a little bit more advanced, but that has a lot more information, okay? And there is another book by Bishop, okay? I think it's Pattern Recognition and Machine Learning. Okay? Those are the 3 books that will cover almost all the material that I am going to be talking about, okay? And I will try to, in the syllabus, I will try to put these chapters on the syllabus so for your, for reading material, okay? But there are, I should just say this. When I started this class, I couldn't find one book that will be appropriate. Okay? So most of these books that I've mentioned have been used for graduate courses. Okay? There are very few books that are for undergraduates. Okay? And it was very difficult for me to judge your background, and I couldn't find an appropriate book to tell you, to say that's the shortest answer. Okay, so I have a mixture of things and my lecture notes, and there are plenty of references on the internet. Okay, so I'm sorry that I am not providing you with a good textbook and following that textbook, because I couldn't find an appropriate textbook for you. Yes?
Is it fine to buy just introduction to machine learning, because I don't have that much money.
Pardon?
I don't have many money, so
Most of these books are downloadable by, it's PDF. All of them. I think most of them. It's free. Okay? So you don't need any money for that. Yeah, that's good. Okay? Yes. And there are a lot of programs. There are videos. And you should be using these things. Okay? Okay, so let me just go over what I'm supposed to cover today, which is decision tree. Let me just decision tree. Okay, that was a review, and this is sort of what we're going to cover. So let me just start off. Decision tree, sometimes called CART. Okay, classification and regression tree. Okay. It's one of the most popular methods. Okay. Oops. What happened? Says- huh? Oh, okay. Oh yeah. We got it. We got it. Okay, and it's popular because it follows human level thinking. Okay, we went through this. It's composed of nodes and branches, and we're going to go over it. Nodes represent features, okay, and branches represent decision. Okay, and there are also at the end you have the outcome. Oops, sorry. So this is an example of decision tree. Okay, and you have two dimension x1 and x2. Okay, two-dimensional data. I should just like to say that input data and feature are, I'm going to use that without any distinction, but there is the distinction between data and feature. What you would like from the data to extract out features that's going to be relevant for classification. Okay? So we saw an example of movie, okay, various movies, and we extracted out feature. Okay? But I'm going to be using feature and data, without distinction. Okay? Okay, so this is a tree decision tree and you see these nodes and there are branches, that says yes or no to that, each one of them. Okay? And at the leaf, it's the outcome. Okay, so you have a two-dimensional data, and if the point lies here, then any point that lies here gets the value v1. Any point that lies here gets value v4. Okay? So you're grouping. I'm going to look at classification trees. Okay? Decision trees are used for classification and regression. Okay? So I had 14 data here, and as I said, this is a subset of the number of data that that may be that we need to know. And I also like to say that, okay, so you have, so the outlook is, it's sunny, it's very hot outside, and it's humid, and there's no wind, so it's probably very dangerous for kids to go out and play, so there's no play. Okay? So this is the type of thing. I would also like to, it's going to, someone asked me a question right after class about my next example. So there are 14, and the possible number of combination is 36. Okay. Now, this is just data. This is the label, but this label can be noisy. Huh? What do I mean by that? Noise can enter in many ways. Someone who's recording this may erroneously label them incorrectly, or let's say a teacher administrating this play and no play may not follow a certain rule. Okay? So it's 14 days. Just think about 14 days. Sunny, hot, high, no. And that particular day was no play. Okay? But under a similar condition, you may have what? Okay. On another day, you may have play. Okay? So do you understand what I'm saying? So, let's say I gave you all 36 days with all the combinations. That's it, you may say. Okay, because we went through all the combinations. But there are noise. Okay? And in machine learning, without regards to all the combinations that we have to learn, without regards to all that combination, we just take this thing as data and try to find the best possible path. Okay? So I hope everyone's clear on this. Okay? So we have this, and I gave you an outcome of this decision tree, this example and that example. And if these two decision trees gave similar results meaning that on test data it performs similarly, which one would you choose? This comes from the very first lecture. We would choose a model that is simple. Okay? Now, determining whether a model is simple and complex, that's another topic. Okay? But just by looking, there's more branches and more nodes in this thing. Okay? And we would just say that this is with various measures of complexity of or capacity meaning the model complexity, this one would probably come out having more complexity, okay? So, generalization. Okay, now, so let's look at some examples of doing decision tree. The main principle is this thing here. So, we are doing splits. We're splitting into, in this example, 3 ways, 2 ways, various ways. And we want to do the splits or partitions such that it leads to splits that are pure. Okay? Pure meaning homogeneous. Okay? Now, homogeneity and pureness, there are various measures for this. And I'm going to be talking about, there are various measures, and I'm going to be introducing 2. Okay? One is based on entropy, and the other is based on Gini index. And there are various ways to improve this decision tree to make it to perform better. But we're not going to be talking about this because this is an introductory course. So first approach, information theoretic approach. An object or has a certain information. Okay, and we're talking about this information. And after revealing certain attribute, okay, the leftover information. Okay, so from yesterday's term or Wednesday's term, I said something about uncertainty. Information is uncertain. Uncertainty, measure of uncertainty. After observing certain attribute, so here you're not observing the label, but certain feature of the data, then your uncertainty is reduced, okay? But whatever is left over, we call that residual information. And the gain of an attribute is represented by the difference between before and after, okay? And what we're going to do is, most important attribute is the one that minimizes this this residual information, leading to maximum gain. So, entropy, I've defined this. I'm not going to go talk about this. Okay. C is class, by the way. Okay. The label. C is the label. Okay. So make that sure. And I went through this picture right here. Okay, yesterday. Understand these 2 corners. When something happens with probability 0, the entropy is 0. When certain thing happens with sure probability 1, that's 0. When so I'm talking about binary class. When probability is 0.5, when something happens or not happen with a half, then the entropy is 1. So it's half times log of base 2, 0.5 plus half times log of base 2, 0.5 and minus sign like that. Okay? This leads to -1. This one leads to -1. And you get 1 value. Okay? So we did that. residual information can be written in this complicated mathematical form, okay? But it's, so what it is, mathematically, this is entropy, okay, or information, right? After observe, so here V represents the value that A takes. So the attribute I'm going to be talking about. So it's a windy, yes, no. V would be yes, no type of thing. Okay. That's entropy, and this is the probability of selecting that attribute, and you sum over that. Okay. And this looks complicated, so we're going to go over some examples. So here are triangles and squares. Okay, so let me look at this. Here it is. So various blocks, red block, red triangle. So I have different colors, different outlines, and there's some dots, not dots, and the shape is triangle or square. There's two. Okay, and so this is the label or the class. Okay, that's the label. That's the class. And I'm looking at 14. And someone came up to me and said, "Oh, look, the color. There are 3 colors. The outline is 2, and dot is 2. So there's 12, and there's 14. I've seen all the combinations. Okay, what's there to learn? Okay, and as I said before, this label, we're assuming that there is noise. Okay, so we're not following a rule, perfectly. Okay, so I just want to make so we can have more data than what's possible. Okay, and there can be some conflict, as I mentioned before. Okay, so we start out with what's the information in this thing here. What's the information? There are 5 triangles, 9 squares. So there are 5. So I'm going to call triangles B and squares as A. So probability of square is that. Probability of triangle is that. Okay? And so what is the entropy? And that's represented here. Okay? That's the information. That will be revealed. Okay? Now, so this is I'm going to be talking about 2 techniques of obtaining this decision tree. The first one is based on information theoretic. That's what I'm going through. And what I want to find out is what type of attribute am I going to, which attribute am I going to select to do the first split? Okay? So there were 3 types of attributes: color, outline, and dots. Okay, and I need to compare. Which is better? Which one leads to a more pure subsets? Okay, so before the partition we have this. Now, based on the color, so after we do the splits, there is red. How many, what is the information here? There are 3 squares and 2 triangles. So that information is 0.971. Okay. And for green, there are 3 triangles and 2 squares, so that's 0.97. Again. But for the yellow, it's all squares. Okay? So there is no uncertainty, it's just squares. So that's 0 bits. Okay? Now what I've calculated here is going back to this equation right here. Oops, where is it? Going back to this equation right here, what I've calculated is I'm looking at A as color, and V can take on what was it? Green, red, and yellow. And for each color, I've calculated this portion right here. You understand that? This portion right here is that value right here. Okay? Everyone understand that? That's the entropy based on given color. Okay? So now we have to find out what the residual information is. So, and we find that there are 5 reds. So the probability of going here is that. For green, 514, yellow, it's that. So the residual color is this multiplied by that multiplied by that, and that multiplied by that. And that's the average information that is, or average uncertainty that's left after splitting it up into colors. Okay? Everyone understand that? Okay? So what do we need to do? We need to figure out what the gain is of the attribute color. Okay? And the gain is going to be that. Okay, so we started out with this. This was the residual, and from splitting the data in terms of the attribute, we reduced the uncertainty by that amount. Okay? No problem with that, that's easy. We need to do this for what? For all the attributes possible. Okay? And what was all the attributes possible? Was color, outline, and dot. And we look at the values. And which one gave you the most gain? The color. The color, by dividing or splitting it up into color, we've reduced the uncertainty by that much. Okay? You understand what's going on right here? So dot and dot and color and so forth. Now we can keep on going. So the first thing was color. For each node, we have to go through that process again. Is it going to be dot, outline, or what was it? What? Color, right? Oh, color has been used, so it's either those two. Okay, and then we go through the gain again, and we can do this. Until we have pure label at the leaves. Okay? And so this was a decision tree that we got. Okay. But there are some problems. Okay. Why do you think color gave you the best split? Why do you think there was you got more gain by splitting in terms of color? Yes.
There was one that was completely pure. One subset was pure.
Yes, but that it just happened, right? It's happened. That's a good observation, but it just happened. So there's something a little bit more that I want to say. We were comparing color, dot, and outline, okay? And color came out 1, gave the most gain. Yes?
There's 3 colors and only 2 types of outlines and 2 types of
Yes.
dots were not included.
Yes, exactly. So if a certain attribute had more possibilities, then obviously that you're going to get more gain that way, right? So color made it into 3 splits. Let's say you had an attribute that had, many more splits. That's just probably going to give you more information gain. Okay? So, is that good? That's something that we would like to avoid. We would like to compare things on equal grounds. Okay? On equal grounds. So IRes favors attributes with many values. Okay? Such attributes split into many subsets, and if these are small, they will tend to be pure. If they split it up into smaller ones, then they're going to be pure anyways, right? So instead of the problem that you mentioned, we're going to look at information gain ratio. Okay? And what is that? We're going to normalize it by the information provided by the attributes. Okay? Here's the amount of information needed to determine the value of an attribute. We're going to normalize it by that. And so if we went through that process again, okay, here is what we started out with. Okay, so IA. Let's say for color, it would be 1.58. So this is, I believe this is red. This is green, and that's yellow. Okay, this operation right here, and then we normalize it 1.56. Anyways, so even with normalization, okay, it turns out that color gave you reduced the information more. Okay, so the color split into 3, outline 2 and 2. The gain was that much more. But the gain ratio, as I said, if you have more splits, this one has more splits, so there's more. This one has more an advantage. So in order to, we normalized it with gain ratio, and the difference or the gain has been reduced, but still, color comes up top. Okay, so this is one way, information theoretic way. Now I'm going to introduce another measure, which is called the Gini measure, okay, or Gini index. And it's represented by this equation right here. probability of a certain class, I and J, by the way, represents class, and it's this. So what is Gini index? Gini index is like this. You have data, and data of a certain probability or proportion related to the probability of the class. Okay, so we saw that in the red subset we had I think there was 2 triangles and 3 reds. Okay, let's say I placed random label on them. So I have 2 triangles, and 3 squares. Okay? And I placed random labels on them. Meaning, I just say, okay, this one triangle, this one square, square, triangle, triangle. Okay. What is the error? What is the probability of error in this case? Meaning that, so this one is correct. This one is incorrect. This is correct. This is incorrect. So there's error. This one's an error. That one is an error. And all of this is an error, right? What's the probability of error in this case? So I have a distribution of true label. Okay, so here in this case, there are probability of triangle is 5,2. Probability of square is 5,3. And I place random label on them. What is the probability of error? Yes?
1 or 2.
No. I mean, give me in terms of 1 over 2.
Okay, 2 over 5 multiplied with 7.
Can you give me the process, how that works?
For each of the of triangle or square, we should multiply its probability. We are going to give it label triangle or square. Like 2 over 5 multiplied with 1 over 2 plus 3 over 5 multiplied with and then
So the-
the sum.
Okay, I think this is what you're saying. So for a triangle, right, it happens with this probability. Probability of triangle error is 5,2 times 5,3. Right? Or let's just write this 1 minus 5,2. Right? And probability of square error is 5,3 times 1 minus 5,2. Right?
Yeah.
And what is the probability of the total error? You just take the sum of these two. That's the probability of error. Right? This is Gini index. This is Gini index. Okay? So you give it random label, and what's the probability of error? Okay? Now, okay. So, and okay, now, if I apply the attribute A, I could get a Gini index based on that attribute. Okay? And this Gini is the sort of the expected error rate. This is the expected error rate, as I mentioned. So let's go through this example. So here, as I said, there are 9 squares, 5 triangles, and the Gini index is given by this. Okay, and 0.5 times 2. Now, after doing the color split, so let's say for the red happens with this probability, green happens with that probability, yellow happens with that probability, and within the red group, we have Gini index given by here, here, and here. That. Okay? I don't think I need to go through the math here. Okay? And so the Gini index for the color is 0.3, whatever that value is. Okay? So the gain through the Gini index is before and after. And you get that. And you compare color, outline, and dot. Okay. Gini index gain. And you pick the one here again. Color gives you the highest Gini index gain. So you do that split. So based on this Gini index, you can perform splits after split. Okay? And you can get a decision tree. So I've told you 2 ways. One is an information theoretic way. Okay? The other one was based on Gini index. Okay? Now, this is not an optimum way to do the splits. Okay, it's not an optimum way. So these models usually are not the best way to do raw predictive accuracy, but they have considerable advantage of being interpretable. Okay, by looking at the splits, oh, yeah, color is a good split. Oh, then you have triangles and so forth. You know what's going on. I'm sorry. Now, what is a good tree? What is a good tree? Obviously, a good tree is something that's simple, right? You don't want to have lots of nodes. You don't want a lot of splits, okay? And how do you avoid having a large decision tree? And one measure is to penalize the number of splits that you have. Okay? So, what am I saying? You can get trees through various methods. You can come up with your own. You can mix it up. Information theoretic, and then you have Gini. Various ways of obtaining a tree. I mentioned 2 ways. Okay, information theoretic way and Gini way. Okay, which is better? Obviously difficult to say, but you would want a tree that's performing similarly on some test data, but with a smaller number of splits. And how do you get smaller number of splits? You penalize it. So you figure out the mean square error, or the mean square error meaning the error. So this will be like
we have problem with screen, so we will change the classroom.
okay, so at the leaves is you would have the pure splits, right? And that will be the classification result that you would come. So the data come. So that's difficult. So at the leaf, you have some training data that's coming at the leaf, okay? And you would classify that leaf with the majority of the class. No? So if you had 5 squares and 2 triangles at the leaf, that leaf will be classified as triangle, majority. So, and when you have test data that's coming in, you plug it in through the tree and find out which leaf it goes to. Okay, and the leaf is has a class. So for instance, let's say I'm just doing one split, okay? One split. This one will be a square. This one will be classified as triangle. This one will be classified as a square, right? One split. And maybe one split, so although it's not pure here, this might do very well on test data, okay? Or you may want to go split more. Which is better? It's difficult to say, okay? And the way you would compare this with the training data, this with, as opposed to doing more splits here, comparing the two, you penalize the total error. So this one, what's the error on this? Let's say, what would be the error on this one? If my decision tree was this, my final decision tree was this, what would be my training error on this one? This one would be 0. What about the here? 2. There'll be 2 errors, right? Because I'm stating this one as to be triangle. There's 2 errors. This one would have 2. Okay, so there's 2 errors, that's 4 errors right here, okay? And plus, so there's 4 errors, the mean square error will be 4. And I'm comparing, but it would have 1, 2, 3 nodes. 3 nodes, 1, 2, and 3. Let's say that's how I quantify the size of this decision tree. I'm comparing that with some more splits, okay? And in that case, the mean square error is going to go what? If I perform more splits, the error is going to go what? It's going to go decrease, right? But I have to compare. Is it this one, or do I do more splits? Obviously, if I do more splits, my error is going to go down. But am I going to do well on the training error, on the test error? We don't know. But we know that the smaller the size of the decision tree, it's going to generalize better. So there must be some trade-off. Okay? So, when you compare those two with different size tree, mean square error, okay? We saw 4 errors. If we had more splits, it would be less, plus the number of nodes. Okay, so one size with single split and more splits. If you have more splits, this is going to go down, but this is going to go up. So you're making that comparison, okay? And there's an alpha that trades off the size to mean square error. And this alpha should be obtained from validation data. Remember the data that we have to split up. Okay? So this is a decision tree. Okay. And so I could do splits forever, or I could get the purest. Maybe I have a huge size data, and I could really make it really deep. So what is the stopping criteria? Okay, it's very important. You usually have a fixed number of nodes. Let's say I'm not going to have more than 1,000 nodes or 1,000,000 nodes. And how would you 1,000, 100? How would you get these values? 1,000, 100. I'm not going to have size more than 1,000. I'm not going to have a size of 1,000,000. What would determine that? I mean, that would be the stopping criterion, right? So like, how would 1,000 and 100, how do I get these values? So I'm in a company, and I have to go through this, and my computing power. I have a limitation on the computing power. I have a limitation on the memory. So based on that environment, I'm probably going to be limited by the number of nodes, or the speed that I need to do it. So that will determine the number of nodes. I'm not going to go more than 1,000. That will be one stopping criteria. Okay? Everyone understand? Now, in order to get the best possible results, I'm sorry about this, grow the tree as much as you can, and then you merge. Okay? So people have found that grow the tree in an information theoretic way, okay, as I explained, and then prune the branches or the nodes using the Gini index game. Okay, get rid of the branches. Okay. So, what do I mean by pruning without changing mean square error that much? If you can remove the branches, then you remove it. Okay? To your desired number of nodes. Do you understand what I'm saying? Let's say I can only have 5 or 10. Let's say 10. I grow it with 100 until 100 I have nodes. And then I start to prune. Pruning means that getting rid of the nodes without changing the performance that much until I get 10. Okay? So that's a little bit. so we need to move the classroom. This is too much problem. Okay. So this is what I've said so far. This is the size. This is sort of the cost of the tree. Cost. So you have a decision tree. Okay. This is how cost is calculated with some parameter alpha, which is the trade-off between the error. This is the error, and this is the size of the tree. Okay? So as you grow tree, the modulus T means it's sort of the complexity of the size of the tree, and I've quantified this as the number of nodes. If I grow the number of nodes, this is going to go down, but that's going to go up, right? So I need to find a balance. Here, what I mean, NM represents the number of data in that node, of the split, if the leaf. And this is the average error. Okay, average error at the nth leaf. Okay. And what's written here is in terms of, so the example that we looked at was for classification. You can imagine doing this for regression, where the label is a real number. And in that case, you would use mean square error. Okay. So that's about all I have to say. We can skip this. This little bit of graph between entropy, Gini, and so forth. So grow with entropy, information theoretic, and then you can prune with Gini or with Gini. I'm so sorry about this. Prune with Gini. Okay. Sorry. Okay, that's it. Any questions? Yes. Yeah. Oh. 절대, yeah, so someone I asked, so this is tree, okay, and so this, I've defined this as the number of nodes. So it's the size of the tree when I have a modulus. It's the size of the tree, some way. Okay, how do you quantify it? By the number of nodes. Okay. But there are many ways to quantify trees, but that's how I'm going to define it. Any more questions? So I've went over this decision tree far more than I was planning to, but that's about it. Okay? So now I'm going to move on to the next topic, which is so the following 3 lectures will be unsupervised learning. If you remember machine learning, so that was to give you sort of an idea of complexity and performance. Remember what I said? The most important graph in machine learning was this graph. As the complexity increases, your training error is going to go down. So if you have more nodes, if you have a bigger size decision tree, you're going to perform, very well on training data. But what is the objective in machine learning? You want to do well on data that you haven't seen. Okay? So that was an example. And I'm going to talk about unsupervised learning. Machine learning involves 3 topics, or big, if I had to group them into 3 big chunks, machine learning. One is supervised learning, where I have data and label. Then I also, it's unsupervised learning, where there's no label. And the third is about learning a policy. And I'm going to be talking about unsupervised learning, where there's no label. The 3 lectures. Okay? Decision tree was just an example, a very popular classification regression supervised learning method. And just to show you that as you increase complexity, you do this. Okay, so it's 10:10, so someone's going to probably say that, call out to me in 5 minutes to stop the class. So let me just give you sort of an introduction. Okay, this slide, by the way, is uploaded this morning. So it's clustering. Okay, clustering. It's unsupervised learning, and it requires no data. Okay, it requires no label. It requires data but no label, and it's used to detect patterns. Okay. And it does something like this: recognizes certain communities within a large group of people. So what do I mean by this? So I don't know, everyone's familiar with Simpson? Okay. Here is various characters in I don't know, drama, cartoon Simpson. Here's Mr. Simpson and characters, and you can sort of group them into family, not family members, right? So I have a large group of people, and I could group them in a certain way, or so the grouping will be different. So here in this case it's family, non-family members. Here, female, male, different ways of grouping, okay? If you go to a department store, there are lots of items, but these items are grouped in certain ways so that you can locate what you want. So, level 4 is men, female, children, other items. They're grouped in certain ways so that you can retrieve and see these items very well. Okay, so shopping items available on the web into a set of unique parameters. Okay, so this is good. This technique is useful when you don't know what you're looking for. Okay, or the shopping was, you're looking for a particular thing, but let's say you have no label and you want to say something about that data. You have no label, you just have data, and you want to group it in a certain way. So you can group them like this. In other ways, you can group them like that. Like this. And what's very important in clustering, grouping of the data, is the notion of similarity. Okay? Notion of similarity. And in machine learning, very often people use the Euclidean distance as a measure of similarity. So if the feature are close to each other, then you group it, just in terms of distance. Okay, but you can think of many ways. So in the department store, how is it grouped? It's grouped in terms of usage, right? For whom? For what use? Okay. So that's the measure of similarity that's used in the department store. But for your various applications, you would have a different measure of similarity. Okay. Okay, it's 10:14. So let's, if I can go a little bit further. There are essentially two ways of performing clustering. Okay, clustering. One is, it's a flat method where there's no hierarchy. Another method, there is a hierarchy. Okay. So what do I mean by this? So men and female grouping. Okay? These are called partitioning algorithms. There is no hierarchy. Well, usually female dominate men, so they are a little bit higher than us, of course, but you know, you're not laughing anyways. Okay, so this is flat. Here, you may think of a hierarchy situation where, in terms of in the family tree, how close you are. So son and mother. Actually, this is not a very good. I would. This is actually not a very good example. Right here. Just think of this. I'm going to change this. This is should be aunt or cousins. Okay. So they are related more than they. Oh, actually, than brothers and sisters. So not grandparents, but aunt. Okay. So brothers and sisters of your mother. Okay, so they are closer, brothers, and then you can sort of group them. So there is a hierarchy as you group. So there's a small group, local group, bigger group, and then a bigger group. Okay, so that's a hierarchical algorithm, requiring hierarchical algorithm. Something like this will be an algorithm, a partitioning algorithm. And you can form this hierarchy bottom up or top down. Okay. Sorry about this, I will change this. Okay, I stop here. It's over 10:15, no one, good. So you want to start the homework a little bit early? Oh, okay. So we'll try to have the homework as soon as possible, and then when the homework is available, we will. If the class comes first, I will say it. If not, we'll send it. 텀 프로젝트는 벌써 말씀드렸는데. 네, 얘기했어요. 첫 시간 때.